Okay, let's learn some more about arrays. So today we're going to learn about um, heap-based arrays instead of stack-based. So previously we learned about how to um, declare arrays like this, which is you might say something like double array 1000. So that creates an array called AR. I'll give it a better name, like truffles. I like truffles. So double truffles of size 1000. So that's an array of 1000 truffles. So 1000 doubles. And then we can access this like truffles 23 equals 3.6, something like that. So that is what's called a stack-based array, and we'll see what that means. And the new way, I'm going to show you right now, and then we'll kind of motivate why we would want to use this and what the differences are going to be. So the new way, which isn't to say everything now must be done this way, but a new option that we're going to have today is called heap-based. And what it looks like is instead of declaring the array like this, we will declare it like this. So double star truffles. So we use that type when we declare it. It's a pointer to doubles. And that will be with the call to calc. So this, in this case, would be calc for 1000. And then I'm going to run out of room, so I got to put it on the next line. Calc 1000 and then size of double. Okay, so that's the new way that we declare an array for heap-based arrays. Again, we'll see what that means. This is just talking about the syntax right now. And then the important thing to know is that the way that you use it is exactly the same. So we could say truffles 23 equals 3.6. That's great. But then the other thing that you have to do additionally with heap-based arrays that you didn't have to do with stack-based arrays is you need to unallocate them using free. Free the truffles. Okay, so it's a little bit more wordy, a little bit more long to do stuff with heap-based allocation instead of stack-based allocation. But it's going to create an array of size 1000 either way here. So what we want to look at is what are some of the limitations of stack-based arrays that make us have to do this, go through this trouble sometimes, and what are the differences in how they work. So let's look at a program. This program, I'm calling it big.c, is just not really doing much interesting. Just creating an array of whatever size the user asks for, and then printing out whatever happens to be in the beginning and end of that array after it gets created. And right now it's using this syntax, so that means it's making a stack-based array. So let's see what we can do with this program. If we run it, if we ask for a reasonable size, we get something back. Of course, there might be some random values here because the array is uninitialized. But we get that array of size 1000. If we run it again, we'll get another array of size 1000. Has slightly different values sitting in those spots in memory, but that's fine. We can go reasonably large, like we can get an array of size 1,000,000 here, and that works. But if we go a bit larger than this, so if we go for like 11 million, that gives us a segmentation fault. And in fact, any larger size than that is also going to be a seg fault. And what's happening is that as soon as we try to declare this array of that size, if it's too large, then the operating system halts our program right there. There's no way to even check for it. There's no way to say a nice message to the user like, "Ooh, sorry, that size was too big." The program just crashes very unceremoniously. And to think about what, this is 11 million, that seems pretty big. Well, 11 million doubles is what we're talking about. How big is that in terms of memory? Well, each double is 8 bytes, so that is 88 million bytes, or roughly 88 megabytes. Okay, so 88 megabytes, is that a lot? Well, think about it. You probably have watched, you probably have movies on your computer that are much larger than 88 megabytes. You might even have pictures, if they're very big, that are larger than 88 megabytes. So that means that your program can't store a whole movie and modify a movie. No, that's crazy. This computer has, I think, 16 gigabytes of RAM. So it has many, many more times the amount of RAM than what we're able to allocate in this way. And so what we're seeing is the first limitation of our stack-based arrays. And that first limitation is that they're small. So when we use stack-based arrays, the first problem is that if we really want them to be potentially very large, then we can run into issues. Limitations. So the first thing is that they can't get too big. And related to that of what we just saw is that we can't even check the size. Can't even check whether they're too big. Because we just have to try to allocate and then the operating system halts the program if it doesn't work. In fact, there is a way to know, and I'll show you what that is on the command line. If we say ulimit -a, so ulimit tells us what are the limits. There's all these things that are limited by the operating system when you run a program. And the key one here is what shows up right here is the stack size. So every program that you run has a limited stack size. And in this case, on my computer, that's right now limited at 8,000 kilobytes, which is 8 megabytes. So this one is about, well, it's about 10 times past what we could possibly hope to do. So the 1 million doubles just fit here, but when we went past that, it's simply not going to work. Let's look again and think again about our diagram of kind of how memory is laid out in the computer. And this will help us understand what the limitations are for stack-based allocation, and also will tell us what we're going to get from heap-based allocation and why that's able to be a little bit better. So there's my diagram of all of your RAM. That's like all of your RAM memory. And remember from before that we said some segment of this is actually reserved for your program. And in fact, inside your program, the stack space, so you might have some space here for main, like maybe this segment here is for main, and then the stack grows this way. The stack grows down. And the stack means when we allocate more memory in main or when we call functions. So when you call functions, they go here as well. And so again, like we've already seen, if you have an infinite recursion in your program, eventually that's going to use more and more and more stack space until, boom, it hits the limit of stack space, and that's it. Then your program is out of memory and you get a seg fault. Well, the same thing can happen without even having infinite recursion if we try to allocate a huge array, a huge stack-based array. If it's larger than this width, then that's it. Your program will seg fault. The operating system won't let it continue because the operating system won't let it go past that limit. So this whole space here is called the stack space of your program. And so what it's coming down to is that your program starts with a limited amount of stack space, and that's kind of it. That's kind of all it gets. Because it has to be all kind of contiguous and together, and that's an issue. And there's something else that we won't understand better until we start to get into functions with arrays in, like, I think the next lesson. But there's another issue here as well, which you might be able to think of if you think about what we're talking about with the stack, is that we can't return stack-based functions from stack-based arrays from functions. And again, we'll get more into that next class, but if you think about the way that functions work in the call stack is once a function is done, it's done. And all the variables for that function go away. So if you've made a stack-based array inside a function, when that function returns that stack-based array, the space for it is gone. It's going to be used by another function call or by something else. And so you can't have a function that creates an array and returns a pointer to it, because once the function is returning, then the space for that array is done. And so all those things are going to be solved by heap-based arrays. And what I want you to do for thinking about heap-based arrays is think of this like a store to get arrays, or like a seating. Let's think of it that way. So like seating in a theater. Okay, so we have a theater. It's the theater of RAM. And what's happening is that inside RAM, you know that we have this space for your program, but there's a lot of other programs that have their own space, right? So they have their own space, and they're using this chunk. Some are small, some are big. Maybe Google Chrome is using a whole bunch, and your operating system has to use something in here somewhere. So these are all like the space for other programs. And so what the heap-based allocation does is it's kind of like if this was all one row of seats, and you went up to the usher of the auditorium and say, hey, I have me and 11 million of my double friends, and we would all like to sit next to each other. That's essentially what you're asking for when you ask to create an array of a certain size. And so if you ask for something of a certain size, if someone were able to look through all of the usage of memory by other programs in your computer and find a space that'll fit your needs, that would be really helpful here. Because then they could say, I see this gap right here. Well, that's big enough for you. So let me give you that. And now your program can use maybe that space as well. And now that's great. Now your program gets to use that extra amount of space. Or maybe you actually had that amount of space in here somewhere, so it just gives you a pointer to that piece of the memory that was already allocated for it. And the question is, who has this knowledge? Who could possibly help you out with this? Who would be the usher that knows where to potentially seat you? And the usher in this analogy is the operating system. So the operating system knows what memory is available. And I should emphasize that a lot of the things I'm telling you about the way this works are a little bit false, but they're true enough to understand why we need heap-based allocation. So what heap-based allocation is doing is finding a gap, is finding a space in memory that's free, that's available, and giving you back a pointer to that. So you request from these system calls, can I please have this much memory? And then you get back a pointer to that, or you might get back a response that says, no, nothing is available. And so what are these ways to request? Well, it's exactly this call right here, calloc. So this is a call that will eventually call the operating system and say, please give me this many of this size of thing. So in order to use any of these, I should add that we need to include a header, which is stdlib.h. So we've seen that before, like for the rand function. And we'll see that in an example in just a moment. But so we need to use that for calloc and for free. So those both come from stdlib.h. And then the other new piece here is this one, which is saying what the size of that type is. So in this case, it would be 8, but it could be anything else. It's saying how many bytes are there in that type of value. So overall, this particular calloc call would be asking for 8,000 bytes, because we need space for 1,000 doubles. Okay, so let's see this in practice, and then we'll come back and talk a little bit more about what are some of the advantages and disadvantages. Here's our program again, but now instead of doing this the old stack-based allocation way, let's use the syntax for heap-based allocation. So we'll say nums equals calloc, and then we want to say size, and then size of double. And notice that size is just our variable. This could be called anything, but that's the name that we decided to use. And then size of, you'll see that my text editor highlighted this in brown. That's a special keyword in C that is a way of just getting the number of bytes that are needed to store one of this type. So a double takes up 8 bytes, so this size of double will become 8 when we run this program. And then the way that we use this is exactly the same as we could before. So we can just use array indexing like this. And then the other thing that we have to add at the end is to free this. And I'll talk about what that freeing is for in a moment. Okay, let's try to compile this. And we get an error because I forgot to include standardlib.h. So, like I said, you have to include this other header file in order to get calc and free stdlib.h. So let's try again. Great. And now, again, if we just want an array of size 1,000, it's fine. Although you should notice that the numbers are all 0. If we want 1,000,000, it's also fine. But if we want like 1 billion, well, 1 billion might be a bit much. Let's go for 100 million. No problem. Happens instantaneously. And in general, if you're not sure what the size is going to be, if it could be even more than, I would say, a few thousand, then you probably want to use heap-based allocation like with calc. Okay, and then you also notice that everything is 0 here. That's because of this particular function call. There's another version of this that's called malloc that has a slightly different calling syntax that you might have heard of. That stands for memory allocation. But the C in calc, and we are recommending that you just use calc for this class. The C in calc stands for clear. So this is going to allocate this memory and also clear it out to all be zeros. So it's guaranteed to all be zeros when we allocate memory in this way. Then the last thing to say is, what is this free about? Well, let's go back one more time to our picture of memory. Is that when we call calc or things like this to get heap-based allocation, the operating system is looking around of, hey, where is there a free spot available to give to your program? And when you take some later classes like your operating system class or even your systems programming class, you might talk a little bit about the very complicated, sophisticated, and awesome strategies that are used to decide what is the piece of memory that your program should get. But for right now, we're just using this. We just trust it to work. And what that thing needs to know is that if I'm no longer using this in my program, so, hey, I don't want this anymore. I don't need that array anymore. I need to tell the operating system, hey, I'm not using that anymore. And that's when you call free. So free is going to free that memory up so that somebody else can use it. So when I call free, that just tells the operating system, hey, I'm done with this array. You can give it to someone else. Okay, so this is what heap-based allocation is. It overcomes these few limitations of stack-based allocation, but it comes with new difficulties. We have to use this kind of more complicated syntax to allocate it. We also have to remember to deallocate by calling free, and we have to include this header file. So if we're doing very small arrays, up to, I would say, like less than 1,000, then using stack-based arrays is fine. If you have a fixed size or you know that it's going to be small, then this way is going to be effective and fine. But if you need a bigger one, or if you need to, when we get into like returning arrays from functions, then you have to use heap-based allocation, and this is the syntax to use that.